time to give just a snippet on what my PhD project is about. Because of time constraints, I will be very vague usually. Exactly. So maybe first start with Arthur's trace formula. So what are the notations we should use? So G is a reductive algebraic group over the rationals. One also could use a number field. Now let's just restrict to Q. A is the ring of Adels over Q. And this subgroup GA to the power of 1 is not really necessary, but just for the sake of completeness. And then, roughly speaking, Arthur's trace formula, or in this case, the non-invariant trace formula, is an identity between two distributions. The left-hand side is what people refer to be the geometric side of Arthur's trace formula, and the right-hand side is what people refer to be the spectral side of Arthur's trace formula. And I would like to focus on the left-hand side, so the geometric side of the trace formula. And I already did it here without any explanation, but as well as for the spectral side of the trace formula, the geometric side splits according to some equivalence relation. So it can be, it decomposes as a sum of different distributions, and the equivalence relation we find on the rational points of G is this one. So two points are lying in the same equivalence class if and only if their simple parts are conjugate in G of Q. So maybe to just give a small reminder, so on algebraic groups there is this notion of a Jordan-Chevalier decomposition, which means that every element decomposes as a product of a semi-simple element and a unipotent element, such that these two components commute. So there's one type of one particular distribution in this geometric side I would like to focus on, and this is the unipotent distribution. So for this we first maybe need a small remark that if we look at the set of unipotent elements in G of Q, then this forms a equivalence class with respect to this equivalence relation, since then the semi-simple part is trivial, and then the equivalence relation just states that we want to have unipotent elements that are what was it? Are conjugate over to G of Q, and this is the case. Oh, sorry, this is not the case, but then the semi-simple part is trivial, and then it's obvious. Yeah, this is what I should say. Okay, so, and then for this class we can look at this distribution, and then we would like to have some information about this distribution. And for the unipotent class, it turns out, Arthur proved it in 1985, that there is this spectacular formula. Okay, maybe you don't think it's spectacular, but then I insist it's spectacular. So it's like a formula in terms of local information. So S here is a finite set of valuations, or finite set of primes, let's say containing the Archimedean valuation. And then this formula states that there are uniquely determined coefficients that depend on S and on U, where U is a unipotent element, and M is a Levy subgroup of G. And then you sum over all Levy subgroups containing some standard fixed Levy subgroup coming from a fixed minimal parabolic subgroup. These factors you don't really have to worry about for now. But what I really want to focus on are these coefficients, really, these uniquely determined coefficients. And in order to get some more information about how this unipotent distribution behaves or looks like, we really want to get some more information about these coefficients. And although it's great to have such a formula, there is one big problem, that although we know that there are these uniquely determined coefficients, we simply don't know what they are in most of the cases. And this is basically a problem one wants to tackle in this area. So one question then now is, what is known? What do we know? So there is a small class of groups for which these coefficients have been computed. So to give an example, if G equals GL2, then Jacquet and Langlands already proved this in 1917 in their work on automorphic representations of GL2, that if we take U1 to be this quite natural looking unipotent 2x2 matrix, then this coefficient turns out to be this vector or this multiple of C of S, where C of S is the constant term in the Laurent expansion of this zeta function at S equals 1. Once again, S is just a fixed set of primes, finite set of primes, and later in 2011, Venus and Lapide proved it once more using really this non-invariant trace formula. And not only for GL2, but also for SL2 and GL3 later in the PhD thesis of one of the students of Venus, Jasmine Matz, we know what these coefficients are in these cases as well. And later in 2017, Werner Hoffmann and Satoshi Nakatsuki coefficients in case of a symplectic group of rank 2. But as far as we know, these are the only class of groups we know the coefficients for, and not in complete generality. So maybe we can focus now on a different problem. Maybe instead of really trying to determine the coefficients, maybe it's better to focus on an asymptotic bound of the coefficients. So, for example, if we fix S to be just the set of Archimedean value and just one fixed prime number P, can we then get some understanding on the behavior of these coefficients as P goes to infinity? And if one then goes back to these coefficients, for example, in the case of GL2, then it's actually not that hard to show that they are of the order of log P. Since if we just go back to these coefficients, in the case that S is just this one prime number P, the zeta function is nothing more than the Riemann zeta function times 1 minus P to the power minus S. And then one can compute this constant term, and then one will deduce that this is the case. And in fact, for SL2 and GL3 and SL3, this is also the case. So a natural follow-up question would be, is it maybe true for any reductive group and any unipotent element other than the identity that we have this bound for some n? And one of the things I'm now working on is to focus on this question in the case G equals this symplectic group of rank 2, basically. And for this group, the coefficients are already determined by Hoffmann and Wakatsuki, as I already mentioned. But unfortunately, the coefficients don't look as nice anymore as in the case of GL2. So in the case of SP2, for example, the coefficients now also contain some Dedekind zeta functions, as well as some Hecke-L functions and some Satoshi Shintani zeta function for binary quadratic forms. So it's really not that canonical and trivial to do this. So this is something I'm working on now. And why should one be interested in doing this? So knowing a bound on these coefficients, we also have a bound on some other terms appearing in this formula that are stated in the beginning of Arthur, would give some more information on these geometric sides of this trace formula, which maybe contribute in solving limit multiplicity theorem, which is a problem that really arises in this area. Then I think that's it. So thanks.